Hello, thank you for coming to see my presentation. My name is Chaeyong Park and I'm graduate student at Posttech, South Korea. I'm going to talk about our paper, Augmenting Physical Buttons with Vibrotactile Feedback for Programmable Fields. This work was done with my collaborator, Jinhyuk Yoon, Seungjae, and my advisor, Seungmoon Choi. Physical buttons are one of the most effective, efficient, and pervasive user interfaces, which are widely used in the world. They provide physical affordance as well as natural and pronounced haptic feedback. However, a physical button presents the same feedback all the time, so it is not easy to use physical button for a programmable interface. Other type, virtual button, displayed on the touchscreen with additional vibration, offer advantages of adaptability, but they lack the physical affordance and clear haptic feedback. To improve this drawback, some researchers modulate the kinesthetic response of a physical button by adding a force actuator. But this system is complex and needs the large costs. Also, there is another approach which augments the feel of a physical button by adding a vibration based on the haptic augmented reality. Here, the haptic augmented reality presents the mixed sensations combined with both real haptic sensation and additional artificial haptic fields. And its concept is similar to the visual AR. When the user operates the physical button, the user feels the original force response as well as an overlaid vibration based on this concept. However, none of the work reported the physical or perceptual evaluation results on the augmentation. Therefore, in this paper, we expand the idea by designing many vibration-augmented physical buttons. Then, we explore the vast design space of augmented buttons to acquire fundamental knowledge on their perceptual characteristics and present a structured and detailed analysis on the perceptual attribute of click sensations. This is overall design of our vibration-augmented button. We use a linear mechanical switch which does not include any buckling response. We also use vibrotactile actuator and put them all into 3D printed housing. Then a user feels the vibration-augmented sensation on the physical button. For vibrotactile augmentation, we design 40 vibration waveform by varying vibration frequency, amplitude, and envelope. For frequency, we selected 4 values to cover the entire range mediated by the 2 rapidly adapting mechanoreceptive neural channels called RA1 and PC channel. For the envelope, we designed 5 envelope functions. In general, keep compression take about 30 milliseconds, and the entire operation is finished in less than 100 milliseconds. So, we choose 3 rectangular envelopes with different durations, and the other to have the same duration of 100 milliseconds, which decay exponentially with different rates. We choose 2 values to make an area of the slow decaying envelope, or half of the rectangular envelope, and that of the fast decaying envelope is a quarter of the rectangular one. Lastly, we use two levels of amplitude, full and half. These are an example of our augmentation technique. Here, we visualize the effects using measured acceleration and force profiles. The next section shows 2 user experiments to investigate the perceptual properties of the augmented button. The first experiment is to estimate a perceptual space, and the second experiment is to project perceptual dimension into the perceptual space. In this experiment, we wanted to estimate the perceptual space that visualized the relationships between many physical and augmented buttons. We used 40 vibration-augmented buttons and 7 physical buttons without any external vibrotactile feedback. All augmented buttons are based on the linear physical button number 41, and the button number 41 is the physical button itself without any vibration. Button number 42 requires a smaller force than the base button. The button number 43 and 44 deliver a buckling sensation. Also, membrane switches with different stiffness are used. The last button, the tact switch, has a unique and strong click feel. To compare the similarity between click sensations, we used the clustering sort method. In this method, the participant compared the feel of all buttons and group them into a given number of clusters based on their perceptual similarity. And then we calculate the pairwise dissimilarity score of button feel and apply the multi-dimensional scaling analysis with the score to find the perceptual space. In here, the perceptual space is an Euclidean space that visualizes the relationship between the feel of the button based on perceptual similarity. As a result, the 47 buttons are widely spread across at the 2D perceptual space. The base button number 41 is represented with a star, and the distance between 2 points means the perceptual dissimilarity between the two corresponding buttons. Interestingly, even though the button number 8 is an augmented button, the dissimilarity score between button number 8 and 41 is greater than that between the physical buttons, number 41 and 47. According to results of clustering analysis, the augmented button and the physical buttons are classified into 4 groups. The base physical button and other linear buttons are anchored the green group. Also, there are augmented buttons which are characterized by high frequency and low energy envelope. In the red group, the augmented buttons have low frequency and low energy envelope. From this group, we can see that adding vibration, shown in paging, creates a similar sensation to mild buckling. Also, those augmented buttons can convey a soft rubber feel. In the blue group, there is a physical button number 46, which gives a highly stiff rubber feel, and the augmented button with low frequency and high frequency and high energy envelope. Through the result, the augmented button with low frequency vibration creates a rubber feel, and the energy envelope affects the stiffness of the button sensation. The last group, yellow, has no physical buttons. Thus, vibration-augmented button with high frequency and high energy envelope deliver unique feels, which are quite distinguished from the 7 physical buttons. To analyze the effect of each design variable, we can also show the centroid of each variable. From the result, vibration frequency and envelope have critical effects. More detailed, the changing vibration frequency makes the centroid from right to the left, and the envelope has a similar effect by translating the centroid vertically. Interestingly, envelope shape and amplitude are much less important. In the second experiment, we tried to figure out a coordinate frame that can explain the point distribution of perceptual space with linguistically meaningful words. We selected 10 words consisting of 7 bipolar adjectives with opposing meaning and 3 unipolar semantic words for material properties. After that, participants rate the subjective sensations of each button using sliders. We project each word to the line and in the perceptual space using multiple linear regression. Each line represents a perceptual axis for the button field, and each button position can be projected to the axis to recover the extent of button sensation with the word. For example, Button number 8 gives a hard, sticky, and blunt feel, and button number 20 gives a sharp, shallow, and light feel. Since the perceptual space is 2D, finding two primary perceptual dimensions is sufficient to represent all the buttons using coordinates. To this end, we choose two lines that have high R-square value and are presented with mutually orthogonal axes. Thus, we recommend the sharp blunt and soft hard as the two main perceptual dimensions for characterizing the perception of the button. Using the primary perceptual dimensions, we can obtain the tendency similar to the experiment one, which related to the vibration frequency and energy of envelope. Also, we can label the perceptual properties of the four button group using the two dimensions. The percept of each button can be represented by coordinate b, h, where b is the button position projected to the sharp blunt axis, and h is the button position in the soft hard axis. We can understand the perceptual relation between various augmented buttons, and this is similar to the HSV model for color perception and representation. For detailed description of the other dimensions, you can find them in our paper. In the next section, we introduce many interaction scenarios with simple and easy vibration-augmented buttons. First, we can design context-dependent buttons to deliver more immersive and engaging experience for entertainment. For example, when we play a game, the gamepad can give a bumpy feel on uneven ground depending on the context. Also, in the soccer game, providing different click sensations during attack or defense state may enable the user to be aware of the current context. For electronic device, augmented button can present the state of the system by providing different key press feedback according to the state. For instance, the feedback can be soft, smooth, and right for call from beloved someone. Also, because touch is very effective modality for our effective interfaces, we can customize button click sensation for each driver in a car. Finally, augmented feedback can be associated with the immediate system response to the user. For example, when an error occurs during key pressing, the augmented button can give different feedback as a notification error with auditory and visual effects. Finally, we suggest major guidelines of effective augmentation for the physical buttons. First, the feel of the vibration-augmented button is well expressed in the two-dimensional perceptual space with the two perceptual dimensions of sharp blunt and soft hard. Second, the vibration frequency is the critical design variable for the feel of the button. Using a high frequency makes the button feel sharper, and a low frequency makes it blunter. Third, the energy of the vibration determined by envelope shape and duration is another primary design variable. Augmentation with high energy envelope increases the hardness, while a low energy envelope increases the softness. Next, envelope shape and vibration amplitude make no noticeable difference in haptic augmentation. So, we can use simple pattern without complex computational cost. Last, the augmented button renders a similar sensation to a real physical button that exhibit material properties or buckling effects. From our observations, for the base linear physical button, haptic augmentation with vibrotactile feedback is a very effective technique in expanding button click sensations. This is the end of my talk. Thanks for watching it.